Well, good afternoon, everyone, or good morning, depending on where you are, and welcome to our monthly SLCan webinar series. We're very pleased today to have David Enns, the sales manager of Antec Controls by Price, to present here today for us on airflow control devices. Dave is a graduate of the University of Manitoba, holding a BSc in mechanical engineering. He's a registered professional engineer with Engineers Geoscientists Manitoba. David has been with Price since 2013 and has a background in hydronic product applications focusing on chilled beams. He's been working with the Antec Controls Group since 2015, focusing on the application of airflow control technologies in both healthcare and laboratory environments. I would remind everyone that if you have any questions throughout the presentation, that if you can type them into the chat box on the bottom of the dialog box on your screen, and we'll certainly get to them all at the end of Dave's presentation. And without further ado, I turn it over to you, Dave.
Thank you, sir. Good morning / afternoon, everybody. So our goal here today is to cover airflow control devices, and specifically how we apply these different types of valves or dampers in the laboratory environment. Now, the reason this is a discussion point, the reason this is a presentation we'd like to give, is that there are several different technologies out there. Regardless of the manufacturer, there are several different types of these valves and dampers out there that seek to do the same job. A lot of them end up with the same end goal. They do accomplish the same final end goal, but the way they get there, the way they mechanically actually control and meter airflow is vastly different when it comes to the mechanical components of the valve. I like to split these valves into two main categories you can see here, and that is mechanically pressure dependent, I'll also call these closed loop valves, and mechanically pressure independent or open loop valves. So really you can split this up as terminal boxes and Venturi valves. Now the goal here in discussing these two, or however you like to look at it, three types of valves, isn't to say one of these types of valves is better than the other. Each one of these types of products has its applications. Each one can be very, very well applied. But again, mechanically speaking, each of them operates fundamentally different. And in a high-speed critical application like a laboratory, that mechanical operation, that actual speed, that performance is of utmost importance. The way these work will determine how our laboratory works. And so what we're going to be talking about today are your typical VAV box. I'll sometimes call these standard accuracy damper control valves. I might call it a terminal unit or a VAV. Those are all the exact same device. We're also going to talk about the high accuracy terminal. These will also sometimes be called a high accuracy damper control valve. These are really just terminal units that are more accurate. Then we're going to draw a little bit of a line in the sand, and I'm going to talk about the Venturi valve. I might call this the VV or an open loop type of valve. These are the three devices you'll see in a laboratory. Again, each one can be very well applied, but each one is different. And so what we're going to do here over the course of the next half hour or 45 minutes is kind of break down how they are different and how to apply them. So we're going to start first with the mechanical operation. My one end goal for today is that the group can understand mechanically the difference between these products. And most importantly, if you look at those three images on the right, really the difference between the bottom two images, because while they look identical, mechanically speaking, those two types of valves are as different as can be. We're going to move them into flow and pressure ranges, really the performance, and really not just to talk about the numbers and how much an 8-inch valve, let's say, can flow, but really talk about how to read this performance data, because again, it is fundamentally different between the two. That's going to lead us then into control methods and accuracies. So just again, how we control these valves to get a set airflow. Say when we want 500 CFM, how do we get there? And then one of the most important parts of this talk is the accuracy. And the number we're going to hear a lot in this discussion is 5%, achieving an accuracy of 5% and what that actually means. Then we're going to move into probably the largest part of the talk, and that is speed of response. In a laboratory, We know we need a high speed of response. We need fast-acting valves. We need containment at all times. But what does that phrase, what does the phrase speed of response mean? We're actually going to break down 4 or 5 different ways to describe that. And that's the part of the talk I like to give the best. Then we're going to kind of tail off here talking about maintenance, sound, and finally, not just coatings, but mechanically what is typically available for these valves. Again, as we go through here, please ask questions on the side panel there, and we'll try to touch on them all at the end. But let's start here with the simplest of the 3 devices, the VAV box, the terminal unit. These devices are truly and typically just a round duct with a damper in the way. The only way to control airflow in a device like this is to move that damper blade. We typically call these a closed loop type of valve. And I say that because we have this cross-flow type sensor, something invasive to the airstream there, measuring airflow. A controller will take that information in and move a damper blade accordingly. If we need more airflow, we open the blade. If we need less, we close it. It's as simple as HVAC can actually get. But that's really the defining features of this device. It has invasive airflow measurement, and it's controlled by a damper. Now, when I say invasive airflow measurement, that port on the front or the inlet side of that valve is going to capture airflow. It's going to be measuring essentially total pressure in this system, meaning velocity and static pressures. And really what this means is this is capturing airflow facing the airstream. So this can be a risk when it comes to contamination. This is a bigger concern on the exhaust side, number 1, but also a bigger concern in healthcare than it is in the laboratories. In laboratories, you don't quite have the wipe down issues you would have in an operating room, let's say. There's no Kleenex or lint or dust or dirt. Laboratories are fairly clean and sterile environments. So while that maintenance aspect is still a concern with a standard accuracy valve, it's not as big a concern. The 2 main concerns you may have with this device are the turn down ratio, which we list here as about 6 to 1, but it really ranges anywhere from 3 to 1 to about 7 to 1, depending on some of the equipment you have here, and the straight run requirement required for these devices. This device, and really the pressure measurement, the airflow measurement we use here, relies really critically on laminar airflow, nice, clean, straight airflow. So we often need 3 to 5 diameters even upstream of these valves and sometimes downstream to get a nice clean measurement. And if we don't have that upstream or downstream straight duct, what can be impacted is our measuring accuracy. And that's the big defining feature. All of this is building into the accuracy of this box you see in front of you. No manufacturer will really claim that the controlled accuracy of this box is plus or minus 5% at all airflows and pressures. That's what we're going to target with the higher accuracy boxes, is 5%. So what I'm saying here is when you take up resolution and accuracy of the controller, resolution of the pressure transducer, the cleanliness of the install, the leakage of the box, when you measure this all together, when you stack it all up, the accuracy typically won't be plus or minus 5%. What that number is, I cannot tell you because it's very dependent on the system and the actual equipment on this box. But for your average application, just temperature control in an office, this box is perfectly fine. When it comes to a laboratory, when we're doing volumetric offset, let's say, and adding up all of our supply and exhaust, knowing that precise flow through this valve is really important. And when that is of such high importance, we will typically look at a high accuracy terminal box. So let's start with this device right here. Again, it is fundamentally identical to the VAV box. There is airflow / pressure measuring in this device, and there's a blade damper to control the airflow. Now, what's different about a device like this, a high accuracy terminal, and I should pause and mention, high accuracy terminals from different manufacturers come in a lot of shapes and sizes. What you see on the screen here is not the only version of a high accuracy terminal or a closed loop valve on the market. This is one variety. But the really defining feature of this high accuracy terminal is it compresses airflow. And really what I'm saying is it generates its own pressure drop. So this does two things for us. The first thing that happens in a high accuracy terminal like the one you have here is when you generate a pressure drop, like we do through that Venturi shape, through that throttling neck, we generate a pressure drop. And what I'm saying is we have a larger pressure drop in this device. And really what I'm getting at is a large pressure drop is easy to measure. It's a very simple fact of measuring anything. The bigger it is, typically within reason, the easier a number is to measure. So what I'm saying is it's easier to measure a meter than it is a centimeter. So in our case, it's easier to measure a few tenths of an inch than it is a few hundredths of an inch of pressure drop. And that's one of the features, one of the principles we rely on here for a high accuracy terminal, is generating a known pressure drop, measuring it, and then controlling airflow. The second kind of defining feature of this device would be the transducer you'll often find in the box, and you can see it on the screen here. The transducer inside a high accuracy terminal is, just generally speaking, of a higher quality. I'm going to come back to this in a little bit. It's easy to say this is a better transducer. We're going to talk about in a little bit what that actually means. With these devices right here, across all manufacturers, the real goal is a plus or minus 5% controlled accuracy, and that's what these can achieve. So if you're trying to flow 100 CFM through a fume hood, these devices should be good to 5% of that number. If you're doing general exhaust, say in a laboratory, and you need 2,000 CFM, this device should be good to plus or minus 5% of that number as well. So it's just a higher level, another echelon here of accuracy that we can achieve with a slightly higher pressure drop. And that's the real penalty we pay here, is a higher pressure drop in the system. So those two devices, as I mentioned, are fairly fundamentally the same. But I'm going to draw a line in the sand as I move to the next device here. And that's the Venturi valve, the VV. The Venturi valve looks identical to a high accuracy terminal. Here at Amtech, just for reference, the part number of that spun aluminum body you see is literally the exact same. So what I'm getting at here is these look like, to the outside world, like they are the same valve. But again, fundamentally, they are as different as can be. All of the internals, and you'll notice as I jump back one slide, all of the internals between these two devices are completely different. And this is where I'm going to start talking about an open loop valve. What I'm meaning is in this device, the real fundamental and defining feature of this device is that it actually doesn't measure airflow in any way, shape, or form. There is no onboard pressure measurement that's converted to an airflow. I'm going to pause and tell you what I just said is a little bit of a lie, but we're going to come back to that in a moment. This Venturi valve right here, in no way, shape, or form, relies on measuring pressure to calculate airflow. What a Venturi valve relies on is that it knows the position of that internal assembly and can relate that to airflow. Now, this can only take place in a Venturi valve at a certain pressure range. So when you're looking at Venturi valves, there's often two ranges of pressure available, low pressure and medium pressure. The pressure drop across a low pressure valve needs to sit somewhere between 0.3 and 3 inches of water column, and on a medium pressure valve needs to sit between 0.6 and 3 inches of pressure drop. And essentially what that's going to guarantee is that this spring and cone assembly you can see here on the right side of the page, what that pressure drop is going to ensure is that the spring in there is engaged. That's the minimum pressure, is we're just pressing on that spring enough. And it's also going to ensure it's not over compressing that spring with too high a pressure. If that is held true, meaning if we have the correct pressure drop across this valve, what we can guarantee is that this little orifice right here, and that would exist all the way around that cone, that orifice right there is of the correct size to flow the correct amount of air. So if you set the lever arm that you can see here at 500 CFM, the position I should say that relates to 500 CFM, we can guarantee, independent of pressure, that you are achieving that flow. That relationship right there, meaning the fact that it's pressure independent, there's no mathematical relationship between pressure and airflow. That lends itself extremely well to a laboratory environment. I'm going to show an example of that in a little bit, but specifically the fume hood environment, specifically a manifolded fume hood, uses that part of the technology extremely well. So really what we've done here is we've broken down two types of valves, mechanically pressure dependent and mechanically pressure independent. Always remember, in anything really with a blade damper in it, any closed loop type of valve, there's only one mechanical system. And unless there is some sort of brain controlling that mechanical system, some sort of controller, these devices will intimately marry together pressure and airflow, meaning at a set damper position, as pressure rises, airflow will rise. There will be no mechanical or natural response, I like to call it, to a change in duct static pressure. That is the complete opposite of how a Venturi valve works. A Venturi valve has two mechanical systems at play. The first is where we place that internal shaft assembly. That's what sets our airflow. The second mechanical system is that spring and cone assembly you can see on the screen now. Meaning, as pressure rises and falls in this system, there's a mechanical, or I like to say, a natural response to that change in pressure. Meaning, without any sort of brain or electronics or any sort of controller, we can maintain a set airflow rate. Again, when it comes to the fume hood environment, this is of utmost importance. And that is typically why you'll hear these referred to as the fume hood valve or lab valves. I've seen lots of schedules on the market that list out laboratory valves. That's typically what we'll call the Venturi valve or the VV. So we've broken down here kind of those two technologies and the three devices. We're mostly here going to be talking about high accuracy terminals now and the Venturi valve. But I want to compare and contrast for you kind of the sizing and really the pressure drop between these three types of devices. So what I pulled up here is very typical information on, let's look at the size 8 box. If you look at your standard single duct terminal, a size 8 can typically go down to about 150 or 160 CFM and might max out at about 800 CFM. Now, if you look right down at the bottom, that can use extremely little pressure. At 0.01 inches of pressure, you can achieve that maximum airflow rate of 800 CFM. Now, I want to pause here. Across all manufacturers, the way this is tested is that the damper will be opened wide open. Essentially, the test requires us to take as much pressure drop out of that system as possible and then measure the pressure drop versus airflow relationship. So reading this chart, when you see the operational pressure as 0.01 inches, able to achieve 800 CFM, in reality, every device in your system, in your building, except for one, will be above that pressure drop. And the one I'm talking about is the very last valve in line. That's the one that will be the most open. That one valve is actually capable of achieving 800 CFM at 0.01 inches of pressure drop. Now remember that, because when we look at high accuracy terminals, again, any closed loop type of valve will be measured the same way. So if you look at the high accuracy terminal we have on the screen here, if you look at, again, that size 8 box, the maximum flow is 800 CFM. But the minimum pressure drop required is 0.15 inches. So the big penalty you can see being paid here is pressure drop in your system. To go with a high accuracy type terminal unit, you automatically have higher system pressure, and pressure costs money. So you might see this as a less efficient device. But there's two things I want to note here. The first is that pressure drop, again, is only at a minimum pressure drop. You need at least 0.15 inches at the wide open damper position for this valve to get 800 CFM. This valve will likely consume more pressure than that in reality. The second thing I'd like to note, because we are always endeavoring to create an efficient lab, is that the turn down ratio on a high accuracy terminal is literally twice that of your standard accuracy box. So instead of 160 CFM, a size 8 box can get down to 80 CFM. And again, in the fume hood environment, every CFM you can turn that fume hood down is about $3 to $10 per year you can save in makeup air, depending on the market you're working in and how much energy actually costs. Now, that is how a closed loop valve is actually rated for performance. That is fundamentally different again than the Venturi valve. And this data here is again fairly generic amongst manufacturers, but what I want to point you to here is that operational pressure. Venturi valves, just generally speaking, do operate at a higher pressure drop. So let's look at the worst culprit, the medium pressure Venturi valve on the right here. At a minimum, you must have 0.6 inches of pressure across that valve, differential pressure drop across that valve, all the way up to a maximum of 3 inches of pressure drop. But the way we read this chart is different. To achieve anywhere from 35 to 700 CFM on a size 8 valve, you need anywhere from 0.6 to 3 inches of pressure drop across that valve. The way to not read this is that to achieve 700 CFM, you need 3 inches of pressure drop. That's just fundamentally not true. You need at least 0.6 and at most 3 inches. So there is sometimes a misconception about how these valves actually work and that they are ultra high pressure drop, when in reality, they are a few tenths of an inch higher than your high accuracy box or a standard accuracy box. But again, one of the biggest drivers of energy savings in a laboratory, and this was actually presented very well at the conference here in Winnipeg a few weeks ago, one of the best ways to save energy in a lab is to turn down fume hood flow. So with a Venturi valve, instead of even 80 CFM, we can turn down a size 8 valve and even a size 10 valve to 35 or 50 CFM. And every CFM you can turn that fume hood down is $3 to $10 savings per CFM per year. Again, this is often why we look at the Venturi valve as the laboratory valve. Now again, we've talked open loop and we've talked closed loop. When we are looking at closed loop valves, as I mentioned, there are a lot of manufacturers out there and there are a lot of different ways to measure airflow. And I want to note here, I'm not saying ways to measure pressure. There are another 100 ways to measure pressure. What I'm mentioning here is across manufacturers, there are just different ways to measure airflow. So in any sort of closed loop valve, there will always be feedback of airflow measurement. Typically in the industry, that airflow measurement is done by either measuring velocity pressure, by using vortex shedding, or by using thermal dispersion. All are very, very common. I would say measuring velocity pressure would be the most common method. Measuring velocity pressure, like I mentioned, can be done in a whole host of ways, whether it's pitot tubes, flow crosses, static ports in the airstream, or orifice rings. All of these are ways to measure or amplify that velocity pressure. Measuring velocity pressure can be extremely accurate, plus or minus 5% accuracy, down to quite a low velocity through that valve. That being said, not all velocity pressure measurements are created equal. Now, when I say that, what I'm talking about is the misconception about error and accuracy, and really specifically the error. Now, what we've pulled up here is a fairly typical 2-inch span transducer with what looks like a very tight error tolerance, 0.5%, but that underlying text is really the important part. This 0.5% is error as a percent of full scale. So what I'm saying here is, say we're measuring 1,000 CFM, and my actual velocity pressure is just under 0.5 inch. The transducer error will always be 0.5% of 2 inches. So you can see there on that first line, my measured velocity pressure might be 0.01 away from my actual, giving me a total of 1.1% error. Not a problem, that's still very, very accurate. Let's turn that box down 2 to 1. We're measuring 0.11 inches of water. But still, notice our transducer error has not changed from 0.01 inches. It's 0.5% of 2 inches. That means our measured value might be 0.01 inches away from the actual value, giving us an error of, I'm sorry, I skipped a line there. Might be measuring 0.12, which gives us an error just under 5%. Let's turn this box all the way down to just over 100 CFM, when the actual velocity pressure you're measuring is minuscule, 0.007 as an example, inches of water. Notice that the transducer error has not changed. So the actual error in this system can be as high as 50%, 60%. There are some out there that are as high as 100% error at full turn down. And so what we're getting at here, kind of the point I'm driving at here, is that that 0.5% number, while it seems very small, needs to be thought of in combination with the type of error. And I say that because another type of error exists. Let's look at that same 2-inch transducer with an error that looks to be 6 times higher, 3%. But this transducer accounts for error as a percent of the current reading. Now, that's a fundamentally different concept. Let's look at the exact same data, and I won't read through it number by number here again, but what you can see here is the transducer error shrinks as the measured value shrinks. This type of transducer, while upfront looks to be worse, actually has a better error percentage as a percent of flow as you turn that box down. This is where, when you're looking at different transducers and how to actually measure velocity pressure, this is what comes into play when we're talking about standard accuracy valves versus high accuracy valves. The type of error and the type of transducer you see on your screen right now, this would be more indicative of a high accuracy terminal. This is part of how we achieve such a high accuracy of plus or minus 5%. Now on to the next technology, vortex shedding. For any of you that have ever, in the summer in Canada, because the rivers are frozen in the winter, and ever driven across a bridge in the summer and looked down at the water, you have seen vortex shedding in action. Vortex shedding is a completely natural phenomenon. As you have a moving fluid and you put an obstruction in the way, you will naturally see repeatable and countable vortices being shed off of that obstruction. So if you look in the water as you pass that quick flowing river, you will see spirals going from the left side to the right side, spinning off of those posts supporting the bridge. That same concept is so repeatable, it can be applied to airflow control and airflow measuring. You can literally count the vortexes that are shed, basically count those pulses or knocks in the airstream, count them up and know what the actual airflow is. Now, that is the upside. It's a natural phenomenon. It's fairly accurate. It's 2.5 to about 10% accuracy, depending on the velocity through the device. The only downside that can be seen with these types of devices, and I don't have numbers to represent with this, but they are typically a little slower than velocity pressure sensors. That being said, that response time likely isn't a driver to the speed of response talk we're about to have for the valve itself. That is a minuscule part of the entire conversation. Another, and I won't say the last because there are more, but the third way we're going to talk about today of measuring airflow is through the use of thermal dispersion. And you might be most used to hearing about this when it comes to pressure measurement, actually room pressure measurement that we do in a lot of these spaces. That same theory, that same technology can be applied to measuring airflow through a valve. Thermal dispersion basically measures the incoming temperature of a fluid. It heats it up by a set known amount, and then it measures the temperature again a certain distance away. The farther away that heat drifts, the more airflow you have. And that's a repeatable and measurable phenomenon. This would likely be the most accurate form of airflow measurement. That type of transducer is the plus or minus 3% of reading accuracy we talked about previously. That's another common one in the industry. Now, what does this look like? All of these technologies, again, regardless of manufacturer technology, all of these are part of a closed loop valve. And one of the things a closed loop valve suffers from, whether it's a single duct box, a dual duct, or whether it's a high accuracy terminal, is low flow characteristics. Basically, the phenomenon we're talking about is crack open or quick opening. Everybody's done this at home. You go to turn the garden hose on and you get nothing as you turn that knob 3 times, and you turn it that 1 degree more and you have a huge amount of flow automatically and instantly. And you can either turn it off or you can open it. There's no middle ground between that crack open number. That's essentially how a blade damper works as well. At some point, you will go from the closed position to the partly open, based on the resolution of the actuator and controller, essentially. And most actuators you see in the field work on about a 1/10 of a volt scale. So on a 2 to 10 actuator, a 1/10 of a volt is 1 movement often. So you can see you'll go from 0% flow to some number instantly. That low flow characteristic is very, very hard to control on these types of devices. And that's just something where we need to design and size these valves, whether it's standard accuracy or high accuracy, to be a little more on the part-way open, basically in that more linear type of response zone right here. Now, what does this actually look like? I keep talking about closed loop valves, and I keep talking about Venturi valves, which are open loop, and how they might be better for the lab environment. And I don't want to say better. I shouldn't be saying it that way. I should be saying different. But I want to kind of paint you a picture here of what this actually looks like. What does closed loop look like compared to open loop? Imagine for yourself you have 3 fume hoods like we have drawn here. Each one is sitting at 700 CFM. Notice there's a blade damper in each of those ducts. There's a high accuracy terminal, let's say. What happens when I close off one of those fume hoods, meaning when I target 200 CFM on one of those valves rather than 700? Instantaneously, there will be a pulse, a pressure pulse through that system, and airflow will automatically and instantly rise in those other 2 valves. And I say that because it must happen. For an instant in time, your fan is running at a set speed, and all of that airflow is being pulled through a smaller orifice than it was before. So momentarily, your flow must rise through that fume hood. The goal of any fume hood is to meet what the manufacturer of the hood says and hit a certain flow at a certain sash position. So momentarily with closed loop valves, you cannot attain that. The fan can be turned down, but more importantly, those other 2 valves can open or close to accommodate that change. But that change takes time. We're going to talk for a second about open loop valves and how they behave a little bit differently in that regard. An open loop valve, number one, typically doesn't shut off entirely, so it doesn't suffer from that crack open you might see in a closed loop valve. But it also doesn't ever measure airflow, so there's no such thing as needing to worry about transducer error or measurement value at any point in time. We are simply measuring the voltage through a potentiometer, and that relates us to the position and the airflow through the valve. So that valve characterization, that opening characteristic of that valve, is much easier to control and see on an open loop valve like a Venturi valve, which again makes it at these low flows a lot easier to control. Now, before I get into what this actually looks like, when I say we measure position and compare that to an airflow, that's not the easiest thing in the world to do. We've talked about measuring airflow and how hard it actually is to do. At some point in a Venturi valve's life, it must be put on an airflow measuring station to relate the airflow through the valve to that position. This is often done in a laboratory that is certified by the National Voluntary Laboratory Accreditation Program, NAVLAP, and is often done on traceable equipment. At Antec, we use a company called NIST. There are a few institutes out there that are all highly regarded, but basically you need to have a third party validate that flow through that rig and that it's just as accurate as you need it to be. That is what a Venturi valve relies on, is that this has been accurately measured on every valve so that we don't need to do it in the field. But knowing we can accurately control airflow independently of pressure in a Venturi valve, knowing that we don't need to measure that airflow, and again, knowing that pressure and airflow, they're not tied together, that there's a natural response in a Venturi valve to deal with fluctuations in pressure. What happens on this same system? Notice these aren't blade dampers anymore. These are Venturi valves. What happens when one of those fume hoods closes down to 200 CFM? What happens again when there's that instantaneous spike in pressure through the system? what will happen is nothing. The other two Venturi valves in the system will remain at that set 700 CFM at all times. And they're going to do that because that spring and cone assembly inside each of those valves will naturally move, will naturally sink farther into the valve to take up more pressure and hold us at that set flow. Now you might be saying this is the exact same response, and you are correct. What's different between a closed loop valve and an open loop valve, between a Venturi valve and a high accuracy terminal, is that one is mechanical and one is done through electronics. And no matter how fast computers get this day and age, or in 2020 or in 100 years from now, no matter how fast they get, a mechanical system will always be faster because there will never be a processor in the way of a mechanical system. And that brings us really cleanly to the speed of response talk. Now, speed of response, and we're not going to dig too far into all of this today. Speed of response is one of those terms that's thrown about the industry to mean a lot of things. It's used in a lot of different ways. And unfortunately, there are a lot of different ways to define speed of response accurately. The first one is just naturally speaking what we talked about, the speed of response of a control system. So a change of sense, how quick until a controller tells a valve to move. There's no spec or code or guideline for how quick this needs to be other than really, really fast. As far as closed loop versus open loop valves go, typically an open loop valve will always be faster than a closed loop valve because, again, there's that processor speed in there that we have to account for. But speed of response can also affect your total travel time. You may ask the question, well, it's good to know how quick until we start moving, but how long does it take to get to the right flow? And that's a very good question. And that number is dependent on a lot of things. With a closed loop valve, there's no relationship between position and airflow in that valve. So we have to move a damper, measure to see if we're right. Move a damper again, measure to see if we're right. And that may or may not work in one movement or 10 movements. So that speed of response can be 1 second or 10 seconds or more. With a Venturi valve, again, there is a true map of what position corresponds to what airflow. So it's fairly simple to say, instead of 200 CFM, I want 500, move there. That will most often be controlled by the speed of your actuator. Actuator speed is the most common way to talk about speed of response. And while it's an important conversation to have, it's not the most important conversation to have. Typically speaking, actuators come in two speeds. Standard speed, which is anything greater than 45 seconds, typically up to about 90 seconds. High-speed actuators are anywhere typically from 2 seconds to 7 seconds. Obviously, a 2-second actuator is faster than a 7-second actuator. But that speed is not the whole story. Again, for a Venturi valve it is, but for a high-accuracy terminal, the speed of the actuator is part of the conversation. The quality of the guess you make about where to go next is the other half of that conversation. So really, when it comes down to the designer of a system, somebody who says, I need a laboratory, I need a high speed, the decision is most often to go high speed or standard speed, not to choose between a 2-second actuator and a 7-second actuator, because that's more of a manufacturer side of the conversation to make sure we can hit the actual prescribed speeds of response we need. And that's where I want to kind of come to one of the last talks we have here. And that's the actual defined by ANSI Z9.5 definition of speed of response. And you can read what's up on the screen here. But really what it says is from the time a sash stops moving, we have 3 seconds or less to be within 90% of the required flow. Basically, stop moving your sash and in less than 3 seconds, be at the right flow. That's a generally accepted way to define speed of response on a fume hood. Unfortunately, ASHRAE 110 in the United States has a similar definition, but they also have the opposite definition. Instead of saying the end of the sash movement is where we start the stopwatch, they started at the beginning of sash movement. So what this can do in the speed of response talk is fundamentally change the time we talk about for speed of response. And I'll show you what that looks like in a moment. But again, unfortunately, there is a third way to define speed of response of a fume hood, and that's by the NEB Fume Hood Performance Testing Standard. And now this standard is a little bit more on the middle ground and doesn't provide as much information. It says, instead of the beginning or the end, start your stopwatch after a change in sash position. Now you may ask the question, is that the beginning, middle, or end of the change? And that's really up to the person testing the fume hood. But what does this actually look like? Let's look at those first two standards here, looking at Venturi valves and then high accuracy terminals. In red, you can see the sash position. In blue here, you can see the actual airflow. And what we need is for the gap between the two black lines to be less than 3 seconds. So with Venturi valves, in accordance with that first standard, we stop moving our sash right here just before 5 seconds, and we hit 90% of our required flow right here, under a 1 second speed of response, extremely high speed. Let's take that same data and use a different definition, however. Notice the blue and red lines didn't move. Instead of starting in the stopwatch at the end of sash movement, we started at the beginning. So a 0.8 second speed of response turns into a 2.5 second speed of response. The exact same data, same valve, same control system, same fume hood, same movement. But the speed of response of one looks about 4 times slower than the other. This is why it is so important to always define how we are going to measure speed of response, whether it's one of the 5 ways we've already talked about. Let's quickly look at the same data for a high accuracy terminal. The exact same thing, but you'll notice that speed of response in accordance with the first standard, instead of 0.8 seconds, can be as long as 1.25 seconds. And a high accuracy terminal measured in accordance with the second standard there, the ASHRAE standard, instead of a 2.5 second response, we get just over a 3 second speed of response. This is where you can see a difference between the Venturi valve and a high accuracy terminal. And you can see the difficulty in applying a high accuracy terminal to a laboratory. All of that being said, these fume hoods can be set up with either technology from a lot of different manufacturers to hit that 3 second or less speed of response. It's very possible. It's done in a lot of laboratories around the world. We're going to quickly talk, I've only got a couple minutes left here, about maintenance and then coatings we might have on these valves. As far as maintenance goes, the simple fact is that if you measure airflow, you are susceptible to contamination. If you don't measure airflow like a Venturi valve, you are much more resistant to contamination. So you will see whether it's a cross-flow sensor or vortex shedding sensors or even measuring with thermal dispersion, that you are susceptible to contamination, and you must employ a cleaning cycle for these types of devices. With a Venturi valve using positional feedback, there's no airflow measurement, so we don't actually ever have to clean these devices or worry about lint or dust or dirt in that airstream. We don't have to worry about this image, and this is a real picture taken by somebody here at the factory of a hospital operating room airflow control valve. This is something you don't have to worry about when it comes to Venturi valves. And I say that because, again, we're not measuring airflow, but we also throttle airflow up to a very high velocity through a Venturi valve. We take an 8-inch duct, pass airflow around a 6-inch cone, throttle it through a Venturi section, and then expand it out the back. It's a very high velocity process, which basically just pulls all that lint and dust and dirt through the valve. Now, the 2 last talks we have, again, with the last minute I have, is sound. Sound is something we all think about in the HVAC industry, and the simple fact is that laboratories, number 1, are loud. Number 2, Venturi valves are very loud as well. You can see the rated NC between a Venturi valve and a terminal box there, and the Venturi valve is about 10 NC louder. The simple fact is your standard accuracy box will be quietest, a high accuracy terminal next loudest, and the Venturi valve will be the loudest of the 3. Typically, if you need sound attenuation, there are a lot of ways to attenuate that, but often custom designed silencers or attenuators are the appropriate move for the Venturi valves. And now the coating, the last few slides I've got. Most manufacturers will spin either an aluminum valve or a stainless steel valve, aluminum typically being more cost effective than stainless. So for your typical supplier exhaust valve, you'd often see an aluminum construction. Now this offers almost no corrosion or chemical resistance. Often where you need a chemical resistance, you'll use either a stainless steel body, which works, or you can use a phenolic coating. Phenolic coating is typically a little more cost effective. It is cheaper to put on than it is to coat a stainless valve. A phenolic coating and a stainless steel body cover a nearly identical spectrum of chemicals they are resistant to. Where there's a gap there, actually, phenolic coating will cover a broader spectrum than stainless, a slightly broader spectrum. And the most important one here are the chloric acids, mainly hydrochloric acids. Stainless steel can't survive that, but a phenolic coating can. So some manufacturers will coat their valves, and actually all metal parts will be coated, not just the aluminum ones. For those applications where you have the really caustic chemicals, hydrofluoric, nitric, sodium hydroxide, among others, this is not an exhaustive list, a phenolic coating in a stainless steel valve, neither will work. Neither will exist actually in a few months if it's got those actual acids in it. That's where some manufacturers will coat with a PVDF coating. A Kynar coating is the name brand often associated with that coating. And they'll also use some Teflon parts because Teflon is actually extremely chemically resistant as well. This is what you might call the Cadillac of coatings. Now, the last comment I'll make here before we open this up to questions is that while a PVDF coating, while these high application coatings are very, very good, they're massively expensive. The coating you can see in that image costs more than the valve and the controls combined. And I don't say that to just impress upon you how much this costs. I say that so that we don't try to use this as a catch-all. A Kynar coating is not the be-all and end-all answer to coatings, because you'll often price yourself out of any sort of project you do have by using a Kynar coating everywhere. I have seen projects that completely halt in the ground because the 8 valves they wanted to coat in Kynar. And they wanted to use Kynar because they didn't know what was going through the fume hoods. Proper laboratory design from start to finish will always involve the customer, the end user, and we will always need to know what is going through these fume hoods and valves. And that is how we can best apply these coatings and best spend the capital dollars we have on the coatings we actually need. So with that, I know we covered a lot of ground today and I kind of cruised through the last little bit there, but if there are any questions, we can open the floor to those now.
Thanks very much, Dave. That was a very good presentation. We really enjoyed it. It's quite exhaustive in terms of the number of variations that you can get to do the same thing essentially.
That's right.
At this point, unless someone's got some questions to key in, at this point I don't have any questions for you. So you obviously educated everybody very well today, Dave.
Wonderful.
Yeah. So I'll, unless there's anyone in the process here doesn't look like it, then we'll wrap this up. Dave, and on behalf of SLCan, I want to thank you very much for your presentation.
My pleasure. And if there are any questions after the fact, please feel free to contact me at antechcontrols.com. You can see at the bottom of the page, my contact information can be found there.
Great. Thanks very much, Dave.
Thank you.
Okay, bye now.
Bye-bye.